Hi everybody, hope you're doing well. In this lecture, I'll give you some recipes for a second quantization or the quantization of a field. It gives rise to something called the quantum field theories. And to learn at a deep level what we will try to discuss here, what you need to learn, okay? So if you want to go at a deeper level, you need to know functionals and functional derivatives. You need to learn about that. You need to learn Poisson brackets for classical fields and also the Lagrangian formulation and the Legendre transformations, because Legendre transformations allow you to switch from the Lagrangian to the Hamiltonian formulation. Okay, so you can just use Lagrangians or Hamiltonians, and in quantum field theories, both formulations are very useful and important. Okay, you need to know about the canonical quantization, which we will do it here in as a practical application. All right, so we'll use a canonical quantization of fields. So you need to know about the canonical variables of a field. And of course, at an advanced level, you would find useful to learn about Feynman's path integral formulation. Feynman, following a hint given in an original paper by Dirac, which is a very important person in quantum field theories, he proposed a very different way of quantizing theories. Okay, so it's a distinct formulation of quantum mechanics. There are the Schrodinger picture, Heisenberg picture, and Feynman formulation is a total different thing. And at a very advanced level, perhaps you need to learn about Feynman's path integral formulation. But here, as I said, we will try to put forward some practical recipes for quantizing a theory, okay, for quantizing a field theory. So we can borrow some ideas from quantization of a classical particle. Okay, so for particles, what we do? Particles, we consider a classical world. So we have the classical here, we have a classical where there are some coordinates, the position coordinates. Okay, let me index the coordinates by some variable k, and momentum by some variable L. Okay, they are functions of time in classical mechanics, but they satisfy some some commutation relation in classical mechanics which correspond to Poisson brackets. All right, so x of k in a Poisson bracket commutated with momentum, some component of position with another component of momentum in classical mechanics lead to a Kronecker delta, KL here, right? And of course, if you commutate using Poisson brackets position with another component of the position vector, it gives you 0. And of course, momentum commutated with another momentum component gives you 0. I'm considering here that this index k runs from 1 to 3, or from x, y, and to y and z, if you are dealing with 3 dimensions of space. Okay, so classical field, classical particle, you have position and momentum, and there are classical commutation relations which are Poisson brackets, right? And quantize the theory, a quantum particle, we need to introduce an additional object, which is the state of the system. Okay, so if you project the state of the system with respect to the basis of position, which is a vector here now in 3 dimensions, okay, you'll find out a function which is a function of position and time. It satisfies some equations, the Schrodinger equation. So in the language of components, you have something like this. Okay, the Hamiltonian is an operator, a differential operator. Okay, but fundamentally, what you need to do is to replace the Poisson brackets by some commutators. You convert position and momentum to some operators. These hats here are, to remember you, they are operators, and they will satisfy the so-called canonical commutation relations. Okay, so any component of the position vector commutates with another component of the position vector. Of course, for momentum components, they also commute with each other, but position and momentum do not commute in quantum mechanics. They are related by, they can be precisely described by the so-called canonical commutation relations. These are the canonical commutation relations. So this is for a particle. For a particle, we have position vector, we have a vector R, which is in 3 dimensions of space x, y, and z, a momentum vector px, py, pz, and some component I will call xl. Okay, so the xk I'm using here. So the x1 is just x, the x2 is just y, the x3 is just the z component. And if you consider x commutated with the operator py here, if the position and momentum components are in distinct directions, they commute. But if you pick up x and px, this will not commute. It will be equal to I h bar. So these are called the canonical commutation relations. Canonical commutation relations. All right. So what we need to do for a field? Okay, for a field, let us borrow these things here, which are the so-called canonical commutation relations. But for fields, I must remember some fields are bosons, some other fields are fermions. So we will introduce a perhaps an anti-commutator for fermions. For bosons, okay, for bosons follow the same rules. They are analogous to the canonical quantization for a particle, but for fermions we need to replace the commutators by anti-commutators. Okay, but just to make the analogies here, what we need to do: fields. Remember, fields are functions of space and time. Okay, they are described by functions of space-time. So a field, let me call a field component. I can have many components for a field. Let me call the field phi some index j. Okay, they are functions of position and time. All right. So in this case, what really plays the role, if I want to borrow some ideas from particle quantization, what plays the role of position? And it is clear that the degrees of freedom for a field are the values of this function here at the position r and at time t. All right, so this plays the role of a coordinate. Okay, this is the degree of freedom. For a particle, the degree of freedom, the degrees of freedom correspond to position and momentum components. Okay, so if you consider this thing here as a particle, you need just to, at time t equals to 0 or at any given instant of time, you need to specify what is the position and what is the momentum. So there are a finite number of degrees of freedom, right? The position of this particle would be 1.5 meters from the ground, and the velocity is 0. But for a field, suppose temperature in this room, the temperature, I need to specify the temperature at this point, at another point, so it's extended over space. Okay, just to remember our first lecture, the lecture at the beginning of this course. Okay, so the coordinates of a field, which corresponds to position for a field, is the value of the function describing that field at the position r and time t. So for a field, I cannot directly use some quantization rules for position and momentum. So for a particle, I replace r, the vector, the position vector, by an operator. Here I cannot do that. R and t are just parameters for a field. So what I need to find out, I need to find out something which corresponds to momentum for a field. So perhaps there is a momentum, okay? There is a momentum, a component k, if the field is not a scalar, because if the field is a scalar, this j here is, you don't need this index for components. But if the field is a spinor, if the field is a polyspinor, if the field is a vector or a tensor, perhaps for a tensor I need more components, more indexes here, but that's okay. For a field indexed by j, I need to find for each, for any j of the field, some momentum associated with that component. So there are components for the momentum, and the momentum of a field also depends on position and time. Okay, so it's also a function. I need to find out a momentum coordinate, or canonical momentum, okay, for a field. This way, if I have something which I can call the coordinates of the field, they are just the values of the field at any given position of space and instant of time. I find out something which I can call it the momentum of the field, and with these two objects, which I can define for classical fields, all right, I can quantize it. I can use a recipe. I can use a procedure in the so-called canonical quantization. I can just use a method for quantizing the field. So this is, I am just anticipating something. This is just the derivative of the Lagrangian. Okay, if you have a Lagrangian for the field, Lagrangian depends on the field, depends on the derivatives of the field, depends on time derivative of the field. field components. So Lagrangian is a function of the field. In classical mechanics, for a particle, the Lagrangian, I'm just anticipating some facts, Lagrangian corresponds to the kinetic energy minus the potential energy. By contrast, the Hamiltonian is the sum of these energies. And the Lagrangian is the difference between kinetic and potential energies. But for a field, you can find out something which corresponds to some kinetic term and some potential energy term. For a field, you can do that also, not only for particles. And therefore the field depends on its components, coordinates, the derivatives, the spatial derivatives. For a particle, you do not need that because particle is just a position depending on time. But for a field, the argument is position and time dependent. And there is something which usually you could eventually for some fields you could interpret as some velocity of the field, but it's not just it's not it's not just direct to identify it as some velocity. Okay? So the Lagrangian, when you derive that function with respect to dot phi j, and this dot here of j, it's interpreted as that thing, time derivative of the field. So usually they use a dot above the variable you are differentiating with respect to time. Okay, if you derive the Lagrangian with respect to the time derivative of that field, you will find out for that given field, you'll find out the momentum coordinates or the canonical momentum for the field. Okay, so for fields, we need to find out coordinates and momentum variables. Okay, a field satisfies some equation, okay, some differential equation. So fields satisfy partial differential equations. Okay, and now we can just by analogy use the same ideas which we borrowed from particles. Okay, so what are these ideas? I can use canonical commutation relations. So let me erase this thing here. So for a field, again, we have some coordinates phi j, which depend on position and time. We have momenta, canonical momenta, which is the plural of momentum. Okay, they are canonical variables. I have some phi of k, they are momenta for the field, which also depend on position and time. And to quantize this thing here, I just replace the function by an operator. The same way, in the same manner, we just replace it, the position by an operator and for a particle, and the momentum we replace it by an operator, okay, which also depend on position and time. But this thing here is something proportional to a so-called, it is proportional to something called a functional derivative. Okay, so a functional derivative, and perhaps you can have a minus I h bar just to make it, you can make it very analogous to what happens for a particle. Remember, for particles, we have momentum as an operator is minus I h bar, the gradient operator or partial derivatives. But now the components are field components, the coordinates, and the momenta of the field are functions. So this thing here is a so-called functional derivative. Okay, I don't know if you can properly see what is written there. Okay, but it's usually these things here can be quantized according to one of the rules, bosons or fermions. So for bosons and for fermions, what you, what you need to do for a so-called canonical quantization, you pick up commutators here. So commutator of a component J at the position R at time t, and the commutator you transform it to operators. Okay, they are operators. So just remember, a classical field is described by a function. Okay, a function is per se what describes that field. Okay, so electric field. What is the electric field at this point? In classical world, it has a value here, a vector valued function at each point in space. In quantum mechanics, what is the electric field? It is an operator acting on some Hilbert space, which will produce on the average an average value which will perhaps satisfy classical Maxwell's equations. But as a matter of fact, what classical Maxwell's equations are, they are some form of averages of the electric field and magnetic field operators. They are operators acting on some space, some abstract space, which in the case of the electromagnetic field would be the photon number. Okay, so the state of the system would be photon numbers, a Fock space describing photon numbers, and the electric field would create or destroy a photon of that field, and therefore it is an operator. That's the meaning of a function for a field becoming an operator. The field itself is not directly measured. What you measure are averages or bilinears of that field acting on something in a Hilbert space. Okay, so this is the meaning of operator. In classical, just to pick up the electric field here, in classical mechanics, electric field is just a function. So it has a x component, a y component, and a z component. They are just components, they are functions of space and time. For quantum mechanics, the component in the x direction becomes a matrix because it is an operator. This, for classical mechanics, is just a function. So it's just a, let me call it a scalar in the x direction. So it's a scalar function, a real scalar function here, and another function for the y component, and another function for the z component. But for quantum mechanics, the electric field becomes an operator which acts on something, yeah, acts on some Hilbert space. And of course, because classical electric fields are real variables, these corresponding to a quantum mechanical operator must be Hermitian. Okay, so it is a matrix. It could be described by some form of matrix, but It's an infinite dimensional matrix, but that's not important. What is important is that it's described. Each component is described by a matrix. So the y component is a matrix. The z component is a matrix, acting on something, acting on some quantum state of the system. It acts classical. The ex component is just a function of space and time. For quantum mechanics, it also is a matrix depending on space and time, but it acts on something. It acts on some state of the system, some psi, which is a state in the Hilbert space. Okay, so this is what is called the second quantization. It is the quantization of the fields. You transform the components of the fields, which for classical mechanics or classical physics are values of the fields at each point, by an operator acting on a measurement of the field in that point. Okay, so it is converted to an operator acting. This operator acts on the physical state, and what you can learn from that measurement, some eigenvalue of that operator. Okay, so you measure the eigenvalues of that operator, and that's the meaning of a field quantization. A field now is replaced by an operator, but since it is a field, this operator is space-time dependent, space-time dependent operator. For a particle, remember that you transform position and momentum to operators, but the position and momentum are dependent only on the variable time for a particle. Now we have something which are the analogies of position, the coordinates of the field. There are analogies of momentum, and these classical functions are position and time dependent, which means space-time dependence. The transformation to an operator makes the operator a matrix whose components of that matrix, of that operator, depend on space and time. Okay, that's the meaning of quantization of a field, right? So for bosons, you just consider that position commutator is zero. The commutator of momenta or momentum components is now in operator. It is also zero, and position and momentum, these are called the equal time commutation relations. It is a classical, it is a quantum mechanical canonical quantization. This is the canonical relations for bosons. They are commutators, okay? And this is equal to I h bar. Analogously for a particle, you put here an I h bar for x and p. X and p, it's I h bar. Now I have phi and pi. You can have components or distinct fields. Okay, so the momentum, the coordinate for a given field, and the momentum for the other field, the commutator is zero. Okay, so distinct fields, if not components of the same field, it could be, this index could be interpreted as distinct fields. Okay, zero for the components of coordinates of the fields, zero the commutator for the components of momentum, and commutator of momentum and, or sorry, coordinates and momentum components commutated at equal times. Okay, but at distinct positions, it could be distinct positions. Okay, so because fields they have values at everywhere in space. Okay, so you could pick a given position for this coordinate and another position r prime for the momentum. So this is just, but equal times, this is just I h bar, a delta corresponding to picking up the same components of the field or the same field, okay? And the delta, which is a Dirac delta, this is a Kronecker delta, and the other is a Dirac delta corresponding to same position. Okay, so it's a three-dimensional delta if you have three-dimensional components, which means a three-dimensional delta of r minus r prime. You must ensure that x is equal to x prime. You must ensure that y is equal to y prime and z equal to z prime. So this is a Dirac delta function in d dimensions if you have d-dimensional space. So for one-dimensional space, you just need delta of x minus x prime. If you have two coordinates in space, you have the product of these two deltas, and for three-dimensional space, you have the product of three deltas. If you have more space dimensions, which is unusual, but in modern theories, you could consider more spatial dimensions, you would have a d-dimensional Dirac delta. So this is a Kronecker, and this is a Dirac delta. Okay, this is infinite for r equals to r primed and zero otherwise. Okay, so for bosons, you consider commutators. So here, bosons, commutators. Remember previous lecture? For satisfying the spin statistics theorem, the symmetrization of bosonic wave functions and anti-symmetrization of fermionic wave functions, you need to use for the annihilation and creation operators for bosons commutators in the relations and for fermions anti-commutators. And this way, you just replace commutators by anti-commutators. So if this is a fermionic field, fermionic fields anti-commute at distinct space-time points, okay, but the same instant of time, just a distinct position in space, okay. So this is vector r, but a primed here, okay. So we primed, and also we have a an anti-commutator for the canonical momentum of that field. You need to find out what it is for the given field, but as a matter of fact, there is usually there is a canonical momentum. If there's not a canonical momentum, you run into trouble for quantization in general, and this is zero. Okay, so components of coordinates anti-commute for fermions, components of momentum anti-commute for the momentum, of course, and if you pick up momentum at a given position at a given time and momentum at another position at the same time, this is equal to I h bar delta, the Kronecker delta here of jk, and the Dirac delta in three dimensions, if three-dimensional space-time, r minus r prime. Okay, these are the rules for quantizing a field. Okay, these are the general rules. So let us just specify what in general are momentum of a field, and let us use the non-relativistic electrons, which is fermionic, as an example of a quantization of a field. Okay? So remember that there is an important aspect which for now assumed to be valid. So real fields are uncharged. They do not have electric charge, do not possess electric charge. Okay, so they are Hermitian fields. For instance, for real fields, a field which is real, for a classical field, it is equal to its complex conjugate at a given position and time. So electric fields, electromagnetic fields are real fields in classical mechanics. Gravitational fields are real fields. Okay, so in classical fields, these are assumed to be chargeless. They are, in fact, photons carry no electric charge. Okay, so this is for classical. If the field is real, it corresponds to a field value at a given position and time is equal to a field complex conjugate of that field at the same position and time. And this for classical mechanics, for quantum mechanics, sorry, you need to replace this by operator, and since the operator is a matrix, can be represented by a matrix, it becomes the transpose conjugated. So it is a Hermitian field, Hermitian, or self-adjoint field. And when you quantize a real field, you need to take care of that. You need to pay attention to the fact that your representation must be Hermitian, okay? But there are complex fields. We will refer to electric charge, but it can also be another types of charges, not necessarily electric charge. A field could be chargeless under the electromagnetic interaction and be charged under possess another type of charge, another kind of charge. But here we will only refer to electric charge and electromagnetic fields for interactions. And usually complex fields are charged. They are charged. They have charges. They possess charge, electric charge for us. Consider it electric charge. Electron field. So to have charge, a field must be complex. And a complex field for a classical field, if you pick up the wave function for an electron, it needs not to be real. So in general, you have that the field is not equal to its complex conjugate for a classical field, but if we transform it to a quantum mechanical operator, this becomes an operator, and this complex conjugate operation must be translated to the transposed conjugated or the Hermitian conjugation, the Hermitian conjugate or the transposed conjugation. Okay, so you need to replace the complex conjugate by Hermitian transposition. Okay, or Hermitian complex conjugation, Hermitian conjugation for short. All right, so complex fields, they are charged, and real fields, They are not charged under the electromagnetic interactions, which is the most important interaction for us. Okay, so if a field is charged, I need to have a complex representation for the field. If the field is not charged, it must be Hermitian. Okay, so phonons in a material is not charged. Electrons are charged, so they must be complex. Phonon, real, Hermitian. Photon, magnon, and okay. But I guess magnon may be charged under another, not electric charge, but I guess magnon is not a good example. Okay, so for real fields, if this thing applies for the field, if this thing applies for the field, usually the canonical momentum is proportional to derivative to the time derivative of the field. Okay, so this is a very interesting aspect. Okay, if the field is Hermitian, so Hermitian field or real field, in proper units, you could do the equality here. So the operator of momentum corresponds to the time derivative. So if the field has many components, this is a matrix, and this is it can be a vector or not only because it is an operator, but it can have many indices. Okay, so it can have many indices. So the index j here corresponds to the derivative of the j component. Okay, and this is for Hermitian fields, so real fields here. Usually you have that. You have that usually. Okay, so for real fields, if this is applied, okay, and for complex fields, if some psi is not equal to the psi dagger, usually non-relativistic field but also for relativistic fields, you could have momentum of that field, okay, momentum of that field proportional to something like I h bar, the dagger of the field. Notice that this dagger here corresponds to a distinct object than this original because the field is complex. So here is a complex field and here is a real field. Okay, so for real field, it is usual, it is typical, but it's not the general rule. Okay, so we'll consider things like this. Okay, non-relativistic electron fields where the canonical momentum is proportional, or in this case, it can be made equal to IH bar the psi dagger. Okay, and of course, this canonical momentum is distinct from this object here. Okay, so far so good. Let us consider an example. So example number 1. Quantize, and when you canonically quantize a field, you usually consider a free field at first. Interactions comes next. You add the interactions after you have quantized a free field, which means non-interacting field, because for non-interacting field, equations are linear. You can solve them by Fourier series or Fourier transforms usually. So let us consider here a quantization. Quantize the non-relativistic electron field. Okay? So what is the electron field for non-relativistic electrons? Well, classical fields, okay, the classical electron is described in quantum mechanics by a field. This field is the wave function depending on position and time. This wave function must satisfy given the Hamiltonian for a free electron. So non-relativistic free electron field. Okay, so the free electron field. So the Hamiltonian in quantum mechanics for the electron corresponds to this thing here because it's a free electron. It does not interact. A free electron does not interact with anything. So free electron. Okay, this is the Hamiltonian. The Hamiltonian only depends on momentum. And for a classical electron, in quantum mechanics become described by this wave function, which is, remember, this wave function is just the projection onto the basis of position of the function evolving in time. So if you pick up Schrodinger's equation, this is for a general state. When you project out this equation into the basis of space, it becomes I h bar, the time derivative of this object, which are the components of this psi projected out to the basis of position. Okay? Basis of position is now a volume integral in 3 dimensions. So this d3r, the notation corresponds whatever the dimensions we put in here is just represent how many integrals we need to do with respect to what kind of components. So these are position components. So this is a volume. Integral means integral under volume means the x, the y, the z, and this integral in the basis of position is just the identity matrix. Okay, so this is the completeness of the position basis. Of course, we are dealing with a continuous basis. So if you project a position to another position, you'll get a three-dimensional Dirac delta. So this is a delta in 3 dimensions. Okay, this is a Dirac delta. And when projected out to the basis of position, you'll find out a partial differential equation. Remember, when you quantize, you first quantize the theory for an electron, a momentum operator becomes this thing here represented in the basis of position. So when you square the minus, you get a plus. I squared is -1. H bar squared is just the constant squared divided by this twice the mass of the particle. And the nabla, when squared, becomes, because the square of a vector is the dot product of the vector with itself, it becomes the divergent of the gradient, and this is just a Laplacian. It is applied to this function. So this is the equation. This is the classical field. It is a quantum mechanical Schrodinger equation for the electron in first quantization because it describes an electron, a single electron, a free electron. So, but from the viewpoint of fields, it is a classical field equation. It is a classical field. This object here is not an operator yet. It is not an operator. Okay? So let us perform the calculations. We want to quantize this equation here. We want to quantize the non-relativistic free electron field. That's what we want to do right now. Okay, so just remember what we can use to solve this equation classically. So first, as a matter of fact, what is the procedure? First step, find out the classical equations of motion or the classical dynamics of the field, which is a classical object. This is the first step, and we already done that. So our object here, it is a non-relativistic electron, free electron, or free non-relativistic electron. What equation this classical field must satisfy? This thing here. Okay. In our case, this is the equation. Well, next step. What you need to do as a second step. Solve the classical equation. Solve classical dynamics using some complete basis functions. Okay? You need to find out the complete basis, and using that basis, try to solve that equation. But in this case, equations for this problem here, usually for free fields, the basis which we can use plane waves. Okay, normally they do the job. They can be used. It corresponds to a simple way to calculate things, but of course you could use for some problems atomic orbitals if you are trying to quantize a situation where you already have here the ionic potentials in a crystal. Of course you can use another types of functions. Okay, but for free fields, usually plane waves, or for almost free fields, plane waves will do the job. Okay, so in this case, some psi of r and t, specifying the k and the omega for that field. It will be some complex constant. It must be subjected to some normalization. So for a given k and omega, you have a plane wave. So this is I k dot r minus omega t. And remember, energy is h bar omega, momentum is h bar vector k. All right, these are from Planck and from de Broglie relation. You need to use plane waves. So if you plug in the plane waves here, you will see you can do it quite easily. And first derivative with respect to time of this equation, you'll find out a minus I omega, but this have already an I factor here, so minus I times I is just 1, and h bar times omega, when you differentiate with respect to time, will produce the energy of the particle. And of course, here you find out minus, but you need to differentiate twice with respect to position. So in this case, remember, for plane waves, the time derivative to the nth order corresponds to I omega to the n, and the Laplacian just corresponds to minus k squared, because the first order derivative is minus I vector k. So if you apply twice, you'll find out minus squared I squared. Let me write it here. Nabla is equal to minus I vector k. I guess you can see it now. So if you apply twice, you get minus squared, which is 1, I squared, which is minus 1, and k dot k, which is minus k squared. So you'll have an h bar squared times k squared, but this is just the momentum squared, so momentum squared divided by twice the mass, which is the h bar squared, k squared divided by twice the mass of the particle. We already know that for a free particle, energy just produces what classical mechanics implies, which is the energy of a free particle in non-relativistic world is just momentum squared divided by twice the mass. Quantum mechanics just produces that result, but you need to have a precisely well-known momentum and energy function. So for a general function, okay, you solved classical dynamics. For a general solution, you already showed that your plane waves satisfy the equation. They are just eigenfunctions of your equation. They are exactly what we need for this problem. Okay, and of course, a general solution for the field will be given by some summation over k vector. Okay, you could sum over spins, of course, because your particle, it's an electron. It has spin, and this spin. So you sum over k. You sum over the possible states of spin, which are up and down. K, as a matter of fact, you need to integrate out because this is a continuous variable, but I will use a summation for the symbol of the integral. It is easy to use in some situations a discrete representation for your field. So for any k and omega here, I need to normalize the plane waves. So I have a 1 over square root of n, some normalization constant here, of course, times the plane wave, I k dot r minus omega t. And since it is a general solution for our problem, I will need to put here constant, some constant which depends on k and depends on the spin. Okay, it depends on the momentum and the spin of the particle. It's not an operator yet. It is not converted to an operator. So the field here is an electron field. The electron field has a charge. I do not, it is charged field. I do not need Ck equal to the complex conjugate of Ck. It is, as a matter of fact, different. And I do not need to make it real. So I do not plug in here the complex conjugate of that part. If I do that here, I will arrive at a real valued field. But for electrons, this is the wave function, and this wave function, sorry, I just touched the switcher here, so I'm sorry, but lights are okay now. And just just to remember, an electron field is a real field, is a complex field because electrons are charged, and this object here are just constants. What we are doing here, we are solving the classical dynamics using plane waves, and remember, what we really are doing here is psi, the object psi of t. This is the solution in Hilbert space, is just a summation over k over spin of some constants, which eventually are not constants, but I can just use the following rule. The coefficients of solutions in the Schrodinger equation are just the ck of 0 times I to the minus the energy times t divided by the h bar here, because I'm using the basis of momentum. So this is for k. I could plug in here also momentum. Okay, so in place of k, I could sum over momentum. Remember, momentum is just h bar k. All right. So wave number or wave vector is analogous, or it is the same as momentum. It just differs by a proportionality constant, which is Planck's constant. Okay, so this is a function of time. This is a momentum eigenstate. And remember that for a general state of a particle, I can sum over the states of a given basis. And now if we project out this onto the basis of position, what we will have, summation over momentum, summation over spins, because an electron is a two-component object, so this, as a matter of fact, I could just insert some spin here, or I can use a two-component vector explicitly, but here I will assume that this representation is inserted inside this object here. It could be a two-component complex component object. So this is a two-component vector representing spin, but for any given momentum here, for any given momentum, I have a given value here, and the spin runs from up and down. So as a matter of fact, the CP of the up state is just some CP function of C1 here and 0. This is the up state, and the CP down is just 0 and some second value here. All right, so I will not write it explicitly. It is implicit in this notation here. Okay, and this is just the basis of momentum, because this is the basis which diagonalizes the Hamiltonian. The Hamiltonian has this operator square divided by twice the mass. Of course, this applied to a momentum basis produces the eigenvalue of that vector times that vector, and this is the energy which we already encountered. Okay, so I can expand the field in terms of a complete basis, which is the basis of momentum in this case for plane waves. And I already know that the coefficients are the same as the coefficients at the instant time 0 times just the phase, because they are eigenstates of momentum for each momentum. So the energy also needs to pick up a sub-index. It depends on the momentum, because for a given momentum, the energy is p squared divided by twice the mass. Okay, so if I project out this into the basis of position, I'll have a Cp sigma. I will drop out the symbol here of 0, remembering this now is the coefficient at time t equals to 0, exponential of minus the energy divided by h bar times t. And when you project out momentum to position, remember this is in the case of a I need to have a normalization here. So it's 1 over some normalization. Okay, let me rewrite it here. When you project out momentum onto position basis, you'll find out apart from some proportionality factor, so it's proportional to exponential of I momentum divided by h bar, which is the k dot r if you are considering 3 dimensions. Okay, so this is it. You have this solution, which is just the superposition of states of distinct momentum projected out to the basis of position. Okay, so this is the second step. The second step, you need to find out the normalization. Okay, for discrete, I need to remember you the following result for discrete basis. We have a summation 1 over n, a summation 1 over n, exponential of n is the number of, is the dimensionality of the Hilbert space, okay? If you consider a Hilbert space running from some minus n1 to a plus n1 with n points in that basis, the momentum is being considered as a discrete basis. We'll find out for this is general, as a matter of fact, for a Fourier series. Okay, this is the discrete representation of a Dirac delta. So for discrete basis, you have a summation from some j running from 1 to n. Okay, from j from 1 to n, 1 over n, I some k minus k primed dot rj, because you discretize momentum space and position space, so this is discrete version. It is just, you need to plug in some discrete values for k and k prime. This is a Kronecker delta k prime. Okay, so if k prime is equal to k, it is a vector, but it is a discrete vector. Okay, so the vectors cannot change. You can have just a set of given vectors, right? You cannot have anything in between these two vectors. So suppose this is k1, this is k2, k3. So these are vectors taking values on a countable set. Okay, so discrete. If you sum up, you have a Kronecker delta in as many dimensions as you have. For a continuous basis, usually you replace these discrete representations by something like 1 over 2 pi to the number of dimensions over 2. The integral in the d dimensions of the suppose position here, you can reverse, you can plug in here rj minus rk and integrate over or sum over k, all right? And the delta will reverse, will be delta with respect to position here. If you integrate now, instead of summing over, if you integrate, and now you have a continual space, it doesn't matter if a plus or minus here, Okay, here also dot r, you are integrating. It will produce the Dirac delta in as many dimensions as you are considering of r minus r prime. This is a parenthesis I needed to consider here. So n is the number of vectors k you are considering, and points are in a discretization of space, basically. Okay, and it is easy to deal with discrete spaces. All right, so I will consider discrete, but remember, momentum is a continuum. Okay, and there is a form at the end of the calculation to just transform a discrete representation into a continuous representation. It is no problem in doing that. So just remember that. And as a second step, we already have done the solution. As a third step, what we need to do, as a third step, we need to just replace the coefficients of the series by operators, operators, and the complex conjugate, which are distinct from the original objects, become the transpose conjugate, and this is operators. And the coefficients in classical fields, so this is classical, they are just coefficients, they become here operators. Okay, what kind of operators? Annihilation, and creation operators. Okay, but what kind of algebra these annihilation and creation operators must satisfy? Well, for fermions, fermionic algebra. For bosons, bosonic algebra. And you can have bosonic charged particles, you can have fermionic charged particles, you can have bosonic non-relativistic particles which have electric charge, and you can have fermionic non-relativistic particles with electric charge. You can have relativistic particles also, but if you follow the steps, first step, find out the equations of motion in classical field equations, solve them using some basis, and expand your solution as a summation in a complete basis. As a third step, you just need to replace the coefficients by operators. Okay, and there must be a generic series for your field solution in the second step. Generic. You don't need to specify what value the C's must have for a given classical configuration. You never do that for quantizing a field. You just say, well, the solutions I can expand into this basis. There are some coefficients. Now replace the coefficients by creation and annihilation operators. That's what you need to do. All right. And in this case, for free electrons, I will use fermionic algebra. Okay. So fermionic algebra, Ck, sigma, which are the labels for, I'll use momentum here. Momentum and spin with another momentum, another value for the spin, 0, which is the fermionic algebra. For the daggers, which are the creation operators, I do the same thing. The anti-commutator is 0. If bosons, if you were dealing with bosons, commutators here. Okay. So bosonic algebra. But here, electrons. So fermionic algebra will have a C of P sigma with C dagger, P primed, sigma primed. It is just for the case of continuum, a Dirac delta in 3 dimensions, or whatever the number of dimensions you're dealing with. So a Dirac delta, and the spin is a Kronecker delta because there are only two possible, so the spin is discrete anyway. But if you're dealing with discrete momentum, you're given a set of momentum variables, you just replace by P prime here. Okay, so it's a product of two Kronecker deltas. Remember, in the previous lecture, we just used it at C of some label I, C to some label, or I guess I used alpha and beta. Alpha and beta, dagger, delta, alpha, beta. So this delta here is a product of two deltas. You need to use the set of quantum numbers here and the set of quantum number here. They must be equal just to have one here and zero otherwise. So momentum P must be equals to momentum P prime, spin is there, they must be equal. Otherwise, you will have an anti-commutator equal to zero. Okay? So this is the third step. You just did that, and now, as a final step, you can just use these facts here to rewrite the Hamiltonian, to rewrite the wave function. So to finish here, because this lecture, I guess, is becoming too lengthy, I will just use the following, the final steps here, just to show you something. Okay, so now I have a psi of R and T. It becomes a psi operator of R and T. The normalization factor is just 1 over the square root of the number of discrete functions in the basis, all right? I need to sum over momentum and spins, so I will use a single summation convention here, but as a matter of fact, this P is summed from the first momentum to the last momentum, and the sum over spins just runs from the up state to the down state. There are just two possible for spin half particle, which is the case of electrons, but we'll use this convention here. This is a discrete basis with n distinct basis functions. Okay, so the coefficients become operators now. Annihilation operators for the function times the basis functions, which if you use another functions, you would use some phi of some other label here, but now we are using plane waves, so exponential of I momentum dot position divided by h bar minus energy times t divided by the h bar. So this is our quantized field. Okay, and there is a dagger field, there is a Hermitian conjugate, which is not equal to that first. Okay, if you need to construct a real field, pick up this field, add this other, you will find out a Hermitian field. Okay, but here we are dealing with a charged field, so I cannot have this equal to that because it is charged. Without proof, I'm saying that. Okay, just accept that for now. This is the transpose conjugated of that operator. This is the complex conjugated of that function. And remember, this is a field. This P here is not an operator, it's just a vector, okay? This energy is not an operator, it's just a vector. The position here is not operator, it's just the value of the position in space, and this is this instant of time. So this is a function in space-time, okay? And of course, the canonical momentum of our field in this case is I h bar the psi dagger, okay? Psi dagger. This is the canonical momentum. This is the canonical field here. This is the canonical field, and our canonical momentum, I just need to multiply this by I h bar. And if you insert this thing here into the general commutation relations at a given instant of time, I will let you, I'll let it as an exercise, leave it as an exercise for you to show that you'll find out if you pick up some component here of spin, say sigma prime here. If you pick up this as spin components, you'll find out delta of sigma prime, and a delta which for suppose discrete values of the position here, discretize the position, you'll find out the delta of r prime here in 3 dimensions. Okay, so this is a Kronecker delta. If you go to the continuum, you'll find out a Dirac delta. But suppose the position is also a discretized space. Okay, so this will become your commutation, anti-commutation relation between this and times the IH bar. So as a matter of fact, if you plug in this momentum here, you'll find out the following. Psi sigma of R and T with psi dagger with R and T, R prime, then T. You'll find out that if you insert the IH bar, it cancels out this factor. You'll find out the following. R primed. Okay, and continuum position space, you'll find a Dirac delta for this Kronecker delta. Okay, so demonstrate that. Demonstrate the anti-commuting relations. For the electric field. Okay. So in the next lecture, we'll discuss a little bit more about this problem here. We don't finish it yet because we need to discuss what is the replacement for averages in this case, what is the number operator, what corresponds to a density, what's the meaning of that, what this operator here really does for a given vacuum. For instance, suppose a vacuum, what this thing produces when applied to some state. Okay, and for now, just demonstrate this thing here. Okay, but we already have performed 3 steps. First, just to summarize. First, how can I quantize a given field? First, find out the classical equations of motion of that field. For Maxwell's equations, they are the Maxwell's equations. Okay? I want to quantize electromagnetic fields. Usually we need to go to something called the potentials, the electromagnetic potentials. But okay, electromagnetic potentials satisfy wave equations. Okay, now that I have the equations of motion for my field, classical field, whatever they are, directly from Maxwell's equations or using the potentials, I can solve classical equations using some given basis, and I can expand the field into that basis, that given basis. Usually plane waves, they are the most important, and in some cases atomic orbitals or molecular orbitals, but usually plane waves do a tremendous job for problems involving free particles in the case of the classical scenario, right? So you solve that, you expanded the field. As a last step, you need to know it is a real field, it is a complex field, because the field is charged under something or it's uncharged under that given interaction. Okay? So photons are not charged. I need to find out the Hermitian representation. Electrons are charged. So I need to find out a complex, a non-Hermitian representation. In this case, we are dealing with electrons. So the psi field must be distinct from the psi dagger. But if you are dealing with some real field and you find out that your original solution is not equal to the psi dagger, just add them up, you'll find out a Hermitian representation. Okay? If real field. If a complex field, you need to make them distinct from each other. All right? And as a last step, replace the coefficients by annihilation and creation operators. Annihilation always come together with the minus I times the energy. And the creation operators always with the minus. Minus is the plus I times the energy times T divided by the H bar. It is a general rule here. Okay? And as a final step in this step, which you replace the coefficients by annihilation creation operators, you need to choose the algebra. Your particle is a fermion, your particle is a boson. If bosons, choose the bosonic algebra for these operators. If your field is a fermion, choose fermionic algebra. You need to choose the fermionic algebra. These operators must satisfy fermionic algebra. And in our example here, we are dealing with electrons, which are fermions. Okay. Next lecture, we will complement some gaps from this lecture here, and see you next time. Bye bye.